All right, so what I want to do today is I want to start off by doing some of the mathematics behind Legos and some of the fun things you can look at. The main theme of this class is not just playing with Legos, but playing with Legos in an efficient manner. This is a little bit different, I think, than what you would do as a 5, 6, 7-year-old. Okay? Out of curiosity, how many people here have taken operations research with me? All right, so just one? Okay. Just one. So I will apologize to you in advance. So what I want to do is talk a little bit about how to do tasks well. All right? In some sense, this is a general life lesson that you can take from this and apply to almost anything. Almost every situation in your lives, you are doing things suboptimally. Okay? A lot of times it doesn't really matter. For the most part, you're so close, it's not going to really make much of a difference. For some things, however, those slight savings will be enormous. For those of you who are thinking of going off into industry, into finance, a 1% savings is huge. Walmart is Walmart because of these 1% savings. They did a better job than their competitors in terms of designing their system to distribute their supplies to their stores. They used a very different model than Kmart. Any fans of Rain Man, the old movie? All right, so you know exactly what Kmart is. So why is Kmart essentially dead? What they did is they put their stores in big cities. Why would they put stores in big cities scattered throughout the country? There are more people there. Walmart started out in the American South in small towns. If you had to choose where do you want to put a store, where do you think you should choose? Yeah.
Small town, real estate is cheaper.
Real estate is cheaper, but you don't have as many people to sell to. Wouldn't you rather have customers than?
In a place that is easily accessible.
So one thing is you want a place that's easily accessible. You want people to be able to get to your stores. But what other reasons might determine where you put your store?
What you're selling.
What you're selling.
What other options there are.
What other options there are. So if you're in a big city, there could be other competitors. If you're in a small city, you might have the market to yourself. Your supply chain. And that's really what made Walmart Walmart. Is Kmart was spread out throughout the whole country. Walmart started off in a small area and expanded. And then they would have superstores, they would have supply depots, and then those depots would serve a bunch of Walmarts around, and the empire would just grow. Okay? Eventually leading to another time. No, sorry. Okay, so in terms of what Walmart was able to do is they did a phenomenal job with resupplying. They had great inventory control. In my mind, one of the greatest inventions of the 20th century is the scanner. If you go to a supermarket and it scans, it tells you how much the price is, but it does more than that. It updates the inventory of the store in real time, and they now know what to restock. They can also correlate purchases. One of my favorite examples of correlated purchases goes to Target a couple of years ago. A father is very upset because he gets some coupons from Target for pregnancy products. And he starts yelling at the store manager, my wife and I are well past childbearing age. My 2 kids are way too young for something like this. Why are you giving me pregnancy coupons? We're very, very sorry. A few days later, the manager of the store calls back and just wants to make sure everything is okay. And the father is very sheepish and says that his high school daughter has had certain extracurricular activities he was unaware of, and the coupons are actually useful. So Target knew before he did that his daughter was pregnant. And the reason they knew is they can look at purchases. And they can look at correlations. If you buy X, you're likely to buy Y. This is extremely useful for marketers now in terms of personalizing things. At the same time, most people do not like to know that they're being targeted. But they want you to be targeted and get you back to the store. So what Target did is beautiful. Is they still want to give you the pregnancy coupons, but they're now throwing a bunch of other random coupons that have absolutely nothing to do with you. They'll put in a coupon for a new grill or something like that. So it looks like you have a mishmash of coupons and there's nothing unified about it. But there's a few key things and then they put distracting stuff around it to hide what they're doing. These small little efficiencies are what make and break major companies. Now here, we're not a major company. We're trying to build a superstar story in 10 minutes or less. But the small little efficiencies we need, these are going to be huge. So one of my favorite examples, and we talked a little bit about it, was Babylonian mathematics. And so this is base 60. So did the Babylonians have the advantage of having beautiful pieces of paper to write detailed class lecture notes like I do? No. What did the Babylonians have to use? Clay tablets. Right? You do not want to lug around a lot of clay tablets. Okay? They are heavy. If you have base 60, that's 3,600 multiplications you need to remember. If you're going to do digit analysis. So need 60 times 60 equals 3600 values. Can we do any better? Do we really need this many? How can we save? Yes?
We can eliminate the ones that are like 2 times 60 and 60 times 2.
Excellent. So as multiplication is commutative, xy equals yx, this gives us 3600 over 2. I'll do approximately. Right? It's, yes?
We can also cut out multiples that aren't of prime numbers.
Let me hold up with that. So why am I saying approximately over here?
Because if x and y are the same, then it doesn't get.
Right, so we unfortunately threw away too many. Because x times x is the same as x times x, because it's the same thing, we've got to add back a little bit. So we have to add back how much? Is it 60 or is it 30? Yes?
30?
It's 30. Because I think we're double counting. We want one of the counts to come, but one of the counts was too much. And so I think it's plus 30. Another way to see it is it's 60 choose 2. So these are binomial coefficients. Is there anybody here who has not seen binomial coefficients? So n choose k means n factorial over k factorial n minus k factorial. It's the number of ways to choose two things when order doesn't matter. Now if I do this, this is the number of ways to choose two distinct things. And then I would have to add in 60 choose 1. So it's either plus 60 or plus 30. I don't really care right now. It's approximately 1,800. That's still a lot of things to remember. A lot more than base 10. So the question is, what else could we try to do to help? Yes?
Well, 60 is easy to break down into factorization. So you basically only memorize the prime.
So one thing is to learn a little bit of number theory and say any number can be written uniquely as a product of primes. And so all I have to do is know my 2 tables, my 3 tables, my 5 tables, and I get my 10 tables for free. So that's definitely another thing we could do. We could do primes. This is getting to be, though, a lot of work, because there's going to be a lot of primes up to 60, but this is still going to be significant savings. What the Babylonians did, which was extremely clever, is they noted the following. X times y is x plus y squared minus x squared minus y squared over 2. If you look at this for the first time, this should look like one of the stupidest things in the history of mathematics. You take a really nice simple multiplication problem, you replace it with 3 multiplication problems, 2 subtractions, and a division. And this is actually a good thing. Why is this an advance?
It's not hard to add things,
It's not hard to add.
which means you only need to remember 60 things. You don't need to remember all the squares.
So adding is easy, good, but I've got 3 multiplications. I had 1 before. They're all squares. So the important thing is, instead of having to know a general multiplication, I just have to know the specific multiplication of squaring. And now I only need a table of squares. That's only 60 things. And now I have division by 2. Division by 2 isn't so bad. And so again, little bits like this, little savings like this are phenomenally valuable in terms of efficiency. This leads to what's called lookup tables. So in terms of how cell phones and other things like this work, you want to minimize the number of computations as much as possible. You want to have things that are already pre-computed that you can then look up and build your answer on. And so this is actually a precursor to, or actually is an early example of a lookup table. It's a lookup table of squares, and we use that to do more involved computations. Your cell phones do this all the time. They have a bunch of values pre-computed in them for various functions, and then they can interpolate and can get other values from something like this. All right. So this is one of my favorite examples of efficiency, of taking something that you may have seen before and trying to find a different way of doing it. All right. That said, none of us would ever multiply like this because we have calculators at our disposal. So I want to talk a little bit about some other possibilities. Any science fiction fans? How many of you have seen the original Wrath of Khan? Possibly my favorite science fiction movie of all time. This had the first example of fractals to be used for special effects. Now it's not a big deal to use fractals in high-level mathematics. I'm actually having lunch with Morgan in the CS department. I can't say his last name because he's in the CS department. He's extremely big in the graphics industry in terms of making stuff like that, special effects. This is a huge field, wonderful interface between mathematics and computer science. What do you think one of the biggest issues in doing good special effects is? The universe is really complicated. Yeah, I mean, Frozen, they had to actually go and play in the snow for quite a while to get a sense of how to deal with all the snow issues. But what other issues would you have in making computer graphics?
Be detailed enough that it looks lifelike, but not too detailed that it takes up a ton of memory.
Excellent. So you've got memory issues, you've got rendering time, you've got computational time, processing time. You want to be able to do all of this stuff efficiently. And so the more computations you have to do, the less detail you're going to be able to provide. So what I want to do is I want to just give you a little bit of a sense of how you could try to do some of these things more efficiently. And again, the goal is not to have you now do these calculations these ways. The computers will be doing all this in the background. I want you to be aware that things can be optimized, that things can be done more efficiently than possible. And when you're given something, don't put blinders on in terms of how to attack it. Really think about new ways of doing things. So, Horner's algorithm. Out of curiosity, how many of you have heard of Horner's algorithm? Okay. Which is good since you took the class with me last semester. I would have been sad if you hadn't. All right, so let's say I give you a polynomial f of x is 4x to the 5th plus 3x to the 4th minus 2x cubed plus 8x squared plus 2x minus 7. We will pretend, just for the sake of argument, that this is the most important polynomial in the world and we need to know its values. Right. Maybe we're using this to figure out what color dots should be in our graphics. If I want to evaluate this at x equals 2 and find the value, what would I do? This is the level of math prerequisites for the course. Good. So plug in x equals 2 to find f of 2. Let's compute and see how bad this is going to be. How expensive is it going to be to calculate this term when x equals 2? How many multiplications do I need?
6.
Not 6. 5. To get x to the 5th, x times x is x squared, x cubed, x to the 4th, x to the 5th times 4 is 4x to the 5th. So this costs me 5 multiplications. How many does this cost? Next one, 3, 2, 1. Okay? So in general, if I give you a polynomial of degree n, it's going to be n plus n minus 1 plus n minus 2 all the way down to 1. That's going to be the number of calculations I need to do something like this. The number of additions is much less. So how many additions do we have? 5. Okay? In general, if we now look at f of x is a n x to the n plus a n minus 1 x to the n minus 1 all the way down to a0, All that changes is the first term, instead of being a 5, is now an n. So we have n plus n minus 1 all the way down to 1, and the additions is just going to be n. One of the reasons I like this problem is it allows us to talk about the most important step, the most critical step. In chemistry, you often do this all the time. Which is the key step in the reaction? Which is the one that takes the most time? Which do you think is more difficult, the multiplications or the additions? Multiplications. Imagine you have two 8-digit numbers. It's a lot more work to multiply two 8-digit numbers than to add two 8-digit numbers. What you can really do is you can break things down into the number of digit operations. And if your numbers are huge, the digit operations for multiplication is a lot worse than the digit operations for addition. Essentially, addition is so cheap with respect to multiplication, we don't even worry about the cost of the addition. It all comes down to the cost of the multiplication. And so the question is, how expensive is the multiplication? It turns out this equals n plus 1 over 2. So we have a really nice formula to calculate how expensive this is. There's a famous story that the great mathematician Gauss was in kindergarten, and his teacher was just having a really bad day. As somebody who's now been teaching for 2 decades, I understand exactly what this is like, and she just wanted to shut the kids up. So she said, add all the numbers from 1 to 100, and was expecting to have a couple of minutes to just relax. And then Gauss yells 5,050. And so there's lots of different ways to prove this. If you know mathematical induction, that's a great way. Another great way to do this is we have 1 plus 2 plus n. Write the numbers backwards. And when we write it like this, what's 1 plus n? N plus 1. And then 2 plus n minus 1 is also n plus 1. They're all n plus 1. And we have n copies of them. So we have n plus 1 n times, but because we added it to itself, we've doubled the answer, so we divide by 2. So the answer is n times n plus 1 over 2, or approximately n squared over 2. This gives you an idea of how complicated it is to evaluate a polynomial. As the degree grows, this gives you an idea of how much more expensive it's going to get. And unfortunately, what this means is that as the degree gets very large, it's going to become very painful to evaluate. A lot of times in math and CS, we don't need the exact answer. If only that were true in building Legos. Unfortunately, we need 10 minutes or less. 1021 was not good enough. But what if we just wanted to estimate approximately how large is the sum? So what if we wanted to estimate? So estimate 1 plus 2 plus n. If you want to be a smartass, this is a great opportunity. Somebody give me a lower bound for this sum. 3. Well, your lower bound of 3 might actually fail if n equals 1. Okay, I did write plus 2. Okay, then I will accept 3 as the smartass lower bound. Can you give me a little bit better lower bound? N. N is a pretty good lower bound. Can anybody give me an upper bound? N squared. So it's at least n. It's at most n times n, or n squared. Because we have n terms and each term is at most n. We have n terms and each term is at least 1. So I could write this maybe in a more enlightening manner as follows. Unfortunately, our upper and our lower bounds are very far apart. So in terms of trying to see what the truth is, we're not there yet. However, we can do a bit better. If we go halfway through and look at the last half, we have essentially n over 2 terms that are at least n over 2. You have to worry maybe a little bit about, is n even or not? If I divide by 2, is there a problem? I don't really want to worry about that in a Lego class. It's at least, say, n halves times n halves, which is n squared over 4. Now that's much better. Now we have our upper bound and our lower bound of the same order of magnitude. If you're interested in seeing how far you can push stuff like this, let me know. I'll put notes on how to do problems like this, how to estimate n factorial. There's a lot of great math in terms of making these estimates. But again, this goes back to what we were talking about yesterday with the extremes. If you look at extremes, you can often get a really good sense of the behavior. And what this tells us is, if we do it like this, it's going to be an order n squared algorithm. Maybe it's 0.25 n squared, maybe it's 0.5 n squared, but it's going to be on the order of n squared operations to do. What I want to do now is I want to show you a much better way of evaluating polynomials. And this is known as Horner's algorithm. And so, this is not, it has a math title, but this is not a full rigorous math class. So what I'm going to do is just prove by example. Is proving by example legitimate? No. Okay. So this is the same as 4x plus 3 times x minus 2 times x plus 8 times x plus 2 times x minus 7. It's not that bad to make this rigorous. I have no desire to make this rigorous. Let's look and see what happens. This is going to become 4x squared, x cubed, x to the 4x to the 5th. The next one will be 3x, x squared, x cubed, 3x to the 4th, minus 2x, x squared, x minus 2x cubed. By grouping parentheses, these two expressions are equivalent. How many multiplications does this cost? 3? I get 5. So we have one multiplication here. 1, 2, 3, 4, 5. Number of additions? 5. So we don't cut down on the number of additions we need, but we greatly cut down on the number of multiplications. If this had been degree 8, this number would have been an 8. If it had been degree 20, it would be a 20. If it's degree n, it would be n. So this replaces order n squared multiplications with order n multiplications. You're basically doing the square root number of steps. This is absolutely phenomenal in terms of what this does for you. And this is one of the key things that allows us to do a lot of fractals very quickly, is instead of these naive ways of evaluating things, we have much better ways. How many of you have taken linear algebra or seen matrix multiplication? Right. I will post something on a faster way to multiply matrices. Just as there are faster ways to evaluate polynomials, there are significantly faster ways to evaluate matrices. And as there are many problems in the world that can be described by applying matrices to systems, the ability to evaluate these rapidly is incredibly important. So again, what I hope you can see from all of this is that you can take something that you've been doing for years, for decades if you're sufficiently old, and you can look at it from a fresh perspective and you can see enormous savings. If you're going to be doing something many times, you want to go for enormous savings. If you're going to be doing something once, is it worth it? It depends on the problem. So I'm a huge fan of math riddles. A couple of years ago, I was at the American Institute of Mathematics, and somebody posed a very interesting math problem. So problem. You have the numbers 1, 2 through 9, and you form A over BC plus D over EF plus G over HI equals 1. Where here, BC means 10B plus C. Basically, I have my 9 digits, and I put my 9 digits in here somehow. And you get the number 1. If anybody immediately sees the answer, please, by all means, feel free to shout it out. All right, can you give me any constraints on where the numbers can go? Yes.
The number 1 has to go in one of the denominators,
Okay, why does the 1 have to go in one of the denominators?
because otherwise, actually, that has to go in can't go in
Why not?
because all the other numbers below it can't divide by
Well, I mean, this means, for instance, maybe it's 2 over 35 plus 7 over 89 plus 1 over, I've got a 4. What am I missing? 6. Maybe I have, some expression like this. Yes.
If you like to get it to actually like all sum up to 1, you would want the bigger numbers to be on the numerator and like 12 on the denominator or something like that.
So let's think, if we only have small numbers in the top, let's say the largest number in the top is 3. So we've got 1, 2, 3. So the best I could probably do is, if I want to make this as large as possible, maybe do something like this. 40, I don't know, it doesn't really matter. Or I could even be a little bit better and say, well, look, if the largest number on the top is a 3, clearly all the denominators will be at least 40 down below, and this is not going to add up to nearly enough. So we know that the large number in the top has to be larger than a 3. And we can keep playing games like this.
B, C, E, F, and H, I must all share some least common multiple that is, I think, less than 100.
Are you positive on that?
I'm not sure if 100, but it has to be less than some value. Just trying to
Or kind of on a similar vein, HI, some factor in HI must be divisible by both B, C, and E, F.
The only thing I worry about is maybe when we add them, somehow the thing in the numerator could then remove a divisor from the denominator. You may be correct. I'm not saying you're wrong. I'm just saying it's a fear I have. What I want you to see is that if you do a little bit of work, you can start to get some idea of how the answer looks. We already know we have to have at least a 4 up top. We can probably improve on this. So when I was at AIM, there's a bunch of the top mathematicians in the world, and they're starting to prove all these elementary number theory results about the restrictions we have on where the numbers can be. I write an extremely inefficient Mathematica code to go through the 9 factorial permutations. And my code is not efficient. My code takes a few minutes to run. It takes less time for me to run the code than it takes them to prove some of the elementary results, and within 5 minutes I have the answer. I only need to run the code once. I don't have to make the code that efficient. And in fact, I could do things a little bit better. When I'm looking at all the different permutations, it doesn't really matter if I call this A over B, C, D over E, F, or if I switch the order of these two, right? That gives me some savings. We talked about this yesterday with tic-tac-toe. Sometimes it's better not to exploit the savings you have because the computers are so powerful. It was easier for me to just write the damn code to go through the 9 factorial orderings than to take into account, let me put in a few more lines of code to fix that. It was running in under 5 minutes. It wasn't worth it. So these are just things to just have in the back of your mind when you're doing problems. If you're only doing something once, you don't necessarily have to optimize too much. If you're going to be doing something very often, if it's going to become very repetitive, then you want to be extremely concerned about efficiency. Okay. Let me move on to one of my favorite algebra problems. Can somebody give me this in lowest terms? 1/4. 19 over 95. 1/5. 49 over 98. 1/2. 12 over 24, 1/4, right? Let's see, 16 over 64, I cancel the 6's, I get 1/4. 19 over 95, I cancel the 9's, I get 1/5. 49 over 98, I cancel the 9's, and I get 4/8, which is 1/2. Right? This is how you divide, right? I checked it 3 times. So clearly, 12 over 24 is 1/4. There is no proof by example. So I just want to put this up as a general warning. Okay? Just because you check something a couple of times does not mean the pattern will persist. Right? This is one of my favorite, simple examples of, the dangers of being misled by small amounts of data. It's very easy to believe you've spotted a pattern. Now, you can prove by exhaustion. And that doesn't mean working until you fall asleep. It means just check every possible case. This is the method of brute force. If you just check every possible case and they all work out, you're done. The goal is typically to try to find a better way than that. Okay, so I just want this up there as a warning on terms of doing things. All right. The last thing is I want to do just one more math thing today. Any other questions on things we've done so far? Okay. So I want to just give one more example of brute force versus high-level mathematics. And this is going to be a combinations problem. And when you think of Lego bricks, you should be thinking of combinations. How many ways can I combine things? What are the number of different structures I can build? Here's one of my favorite problems. I call it the cookie problem. You have 10 identical cookies and 5 distinct grad students. I'm not writing that the graduate students are hungry. That's actually a given. Okay, so for those of you how many of you are considering grad school? All right. The following is not a joke. It's an actual statement of life as a graduate student at Princeton. I was a social chair. I was in charge of our happy hour from 6:30 to 7:30 on Fridays. And we like to tell all the new graduate students that you knew you could be happy from 6:30 to 7:30 on Fridays. Graduate school is really for those who have a passion and a love for the work. It can be quite intense. This is the time when you've really got to be churning things out. I could write hungry. Graduate students are often very hungry. And they are very good at finding free food. When I was a postdoc at Brown, there was a free food email list for the graduate students, where they would send out messages such as, at 4 o'clock there will be a talk followed by the following refreshments. And the guys would go, yeah, I can listen to that for pizza. Or, wait, I'm just getting cheese and crackers? No, I'm not going to do that again. So I'm not going to put in hungry. You should just assume that they're hungry and that they want cookies. I am putting in the word distinct. So this means I'm not talking about an engineering discipline, where we will assume that the professors can tell the difference between their graduate students. This is sadly not always a valid assumption. I had a very shy friend whose professor knew them by the wrong name and did not feel comfortable correcting their professor. I mean, there's 58 of you here. If I get a lot of your names wrong, I think that's justified on the second day of class. When you have 2 or 3 thesis students and you don't remember one of their names, that's pretty bad. All right. What problem do you think I want to concern myself with? Yes? How many ways can I give the 10 cookies to the 5 students? Excellent question. So can you give me a way to solve this? And I don't care how inefficient. Yes?
Does each grad student have to get a cookie?
No. I mean, some of them might be humanities grad students. Oh, sorry. Normally when I'm teaching a math class, it's safe to say that. No, not all graduate students have to. And at the end, we will actually impose the constraint that all graduate students must get at least 1 cookie. Yes? So one possibility is 10 choose 5. And this is all the ways to choose 5 cookies from 10. So what this means is I have my 10 cookies and I've pulled out 5. So that's unfortunately not the same. There's another thing related to 10 choose 5. that seems reasonable. Well, each cookie I have to assign to a graduate student, so it's 5 to the 10. Right? First cookie goes to either you, or you. Second cookie, you. Third cookie, you. Is that correct? Is it just 5 to the 10? Why not?
They're distinct, and you're not just choosing 5 people at a time, and using the side to one person.
Let's just say that again.
You're not just picking 5 people out of the 10 to assign cookies to. You have to assign, you can assign multiple cookies to the same person.
But that allows me to assign multiple persons to the same person. Each cookie gets a label of Alice, Bob, Charlie. I don't know who D is. Maybe David, and then E is Eve.
Because once you give out a cookie, you can't give it out again.
No, that's fine. It's just been given a label. The cookies are identical. All that matters is how many cookies someone gets. This is putting a label on the cookies. So you might remember if I give you the word, this way. Say I take the word Yale, and I ask, how many different words can I make from the word Yale? I have 4 choices for the first letter, 3 for the second, 2 for the third, and 1 for the fourth. Or I have 4 factorial orderings. What state is a horrible, horrible state to have to deal with? I'm sorry? Repeated letters. So which is the one that people normally use? Mississippi. Mississippi. How many distinct words can I make from Mississippi where I use each letter? If all the letters were distinct, the answer is just 11 factorial. 4, 8, yes. One way to solve this is to then put subscripts, I1, I2, I3, I4, S1, S2, S3, S4, P1, P2. If we put subscripts on them, now all the letters are distinct and there's 11 factorial things to do. And now I have to remove the ordering that I've added. So I have 4 S's. And I have 4 factorial ways to order the 4 S's. I would have to divide this by 4 factorial for the S's, 4 factorial for the I's, 2 factorial for the P's, and 1 factorial for the M. 1 factorial is 1 once. I don't really need it, but it just unifies the presentation to write it. This is how many distinct things I can make from Mississippi. If I go through here, because the cookies are identical, it's unfortunately not 5 to the 10. The problem is harder. So can somebody give me a way that will give me a solution? I don't care how inefficient it is. Excellent. And if you do not complete the superstar story in 10 minutes or less, you will be doing this with 100 cookies. A, B, C, D, E. So we start off with 10, 0, 0, 0, 0. We continue until we get with a 10 here. Then we start having a 9 and a 1, 0, 0, 0. And it starts to get to a nightmare when the large number of cookies someone gets is 4, and going through all the different possibilities. This is a pain, okay? But it's doable, okay? If you want to get an appreciation for mathematics, I urge you to do this. Or I urge you to start doing this and then maybe stop when you get down to maybe 7 cookies is the largest number of cookies assigned. Just to get your hands dirty a little bit and just see how bad the calculation is. Okay? I want to show you how to do this problem in 1 line. And this is not just a make-work problem. This idea is actually related to a lot of research I do with undergraduates at Williams. It's related to properties of Fibonacci numbers. It's amazing how many things this solves. How many of you have seen, oh, I should have brought him downstairs. How many of you have seen Sesame Street? Okay. I have heard that certain episodes of Sesame Street are no longer rated G because of a certain character. Which character? You should be able to figure that out based on what we're talking about right now. Cookie Monster. Is Cookie Monster encourages unhealthy eating? And that you are no longer allowed to... I also heard that Oscar the Grouch now lives in a recycling bin, and I have to admit they got me on that one. He does still live in a trash can. All right, I am thinking of the original classic Cookie Monster. What is the one property that you should know about the original classic Cookie Monster? He eats everything, but in particular, yes. There's the great episode when he meets the Count, and the Count wants to count the cookies, and Cookie Monster wants to eat the cookies, and they eventually settle for him counting how many cookies Cookie Monster eats. So we have Cookie Monster. And what I'm going to do, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, is consider 14 cookies. We have 14 cookies, and the original classic Cookie Monster comes, and he eats 4 cookies for us. The difficulty is having Cookie Monster stop at 4. Right? We'll assume we're able to get Cookie Monster to stop at 4 cookies. So let's say Cookie Monster eats this cookie, this cookie, this cookie, and this cookie. So these cookies have been eaten by Cookie Monster. How many cookies are left? 10. There are 2 cookies here, 0, 2, 3, 3. What have we just done? Yes? Yes. It turns out there's a one-to-one correspondence between the number of ways to assign cookies to graduate students and the number of ways for Cookie Monster to gobble 4 cookies from 14 when order doesn't matter. All of combinatorics essentially boils down to counting something 2 different ways and saying one way is the way I want but I can't do easily, the other way is a way I can do easily. And so because of this, we have this beautiful one-to-one correspondence. If I wanted the first person to have 5 cookies, 1, 2, 3, 4, 5, the 6th would have to be the first cookie that Cookie Monster eats. So the number of solutions is just going to be 14 choose 4. Or in general, C plus P minus 1 choose P minus 1, where C is the number of cookies and P is the number of people. And so you have this beautiful one-to-one correspondence. Okay, so any questions in terms of how we solve this with Cookie Monster and combinatorics? It turns out we actually solved a math problem at the same time. And it's called a Diophantine equation. So we solved x1 plus x2 plus x3 plus x4 plus x5 equals 10. Each xi is a non-negative integer. In general, it is very hard to solve equations like this in the integers. There are often obstructions. If I want to solve 2x plus 4y plus 8z equals 1701. How many solutions are there in the integers? None. The left-hand side is even. The right-hand side is odd. So there's an obstruction here. What if I change the 8z to a 9z? Now it takes a lot more work to count how many solutions there are. These equations don't differ by that much, but they have wildly different behavior. Solving things in integers is very hard. What we just did with the cookie problem is we solved this equation, where xi is the number of cookies person I gets. Now, there was a complaint, or there was a question in the beginning, I think complaint was a bit too strong of a language, should every graduate student get a cookie? My personal view is no. Different disciplines are more valuable than others. I have no problem saying this. When I was in grad school, there was a push to have stipends equalized across the board. And I responded with Engineering Appreciation Day. I was paid less than engineers. The engineers were paid more than me because there were corporations that wanted the engineers to be working on projects for them that they could directly use. Why was I useful as a math grad student? I could teach engineering students calculus. And so there really was, in some sense, a pecking order in terms of stipends by how much money are you bringing into the institution. You can argue whether or not this is a good thing or a bad thing. In order to have a happy class, I will not have any arguments, and I will gladly agree that everybody gets at least one cookie. How can we impose this? Well, let's let xi equal yi plus 1. And this will force everybody to get at least one cookie, and yi will now be the excess number of cookies. And this now gives us the new problem, y1 plus y2 plus y3 plus y4 plus y5 is 10 minus 5. Is I just took all the plus ones and moved them to the other side. And so if I require everybody to get at least one cookie, this is now the same as dividing 5 cookies among 5 students. And the answer is just going to be 5 plus 5 minus 1, choose 5 minus 1. If I wanted to require the 5th student to get 2 cookies at a minimum, all I would change is I would subtract off 6 now. It's very easy to put in these minimum constraints. It turns out there's no easy way to put in upper bounds, to say nobody gets more than 4 cookies. Turns out we don't have good ways of solving problems like this. I'll end with one last problem. We're dividing up all 10 cookies among the 5 grad students. What's another possibility? Interesting. There could be issues in cutting up graduate students, so I think I will pass on that. Yeah, I think we want to keep them. Okay. Can a grad student be assigned to multiple cookies? Right. Great. Okay, so that's the key phrase, is you could have cookies left over. And you can interpret what I think your way is more entertaining. But the other way is to say, we don't have to give out all 10 cookies. You know, maybe the graduate students have been a little bit bad. They haven't been working enough on their thesis. They've been playing in the snow. And so I'm not going to put out 10 cookies after tea today. I'm only going to put out 7 cookies. All right, so now we know if there were C cookies, the number of ways to do it is C plus 5 minus 1, choose 5 minus 1. That's the number of ways to assign C cookies. All right. Well, what's 5 minus 1? 5 minus 1 is 4. So this is the number of ways to give C cookies to 5 grad students. And now what would I have to sum over? C goes from what to what? 0. The grad students really upset me and I'm going to give out no cookies today. And it could go all the way up to 10. All right, so what you have to do is you have to calculate 11 binomial coefficients and add them. In addition to combinatorics being about counting things 2 different ways, another way of viewing combinatorics is it's all about story time. And you want to tell a story about what's going on. There's a way to solve this in one line.
Instead of doing this, add one more grad student.
Let's add a professor.
Okay, let's add a professor. And then that professor is like, that if a cookie's in that pot, then no grad student gets it.
Right.
C plus 5.
Right. So now we have 10 cookies, and now instead of 5 people, we have 6 people. Basically, if you only give out 8 cookies, what you can just say is there's a 6th person who gets the unassigned cookies. And so this sum has to be the same as this. So to me, these are absolutely wonderful in terms of being able to take difficult calculations that initially it looks like it's going to take you a while to resolve, and now we can reduce it to something we can do in one line. We can do this now in our head for sufficient years of experience. Okay? All right, so this is going to end the mathematical part of the lecture today. For the rest of it, I want to switch to talking about how to assign the superstar.